All right, now we're going to look at 17.5, which is factors that affect solubility. And the first one that affects the solubility of a salt is the common ion effect. And remember we talked about this before. This is where you add an ion that is already in a solution. So the solubility of a salt will decrease when you add a common ion. And we're going to look here at an example. So for example, okay, if I have this CaF2 equilibrium, so I have dissolved calcium fluoride in water, and I have these two ions, or actually these three ions technically. Well, what happens if I add some NaF? Well, if I add NaF, that's going to break apart into Na plus and F minus. So I'm adding more of the F minus that I already have in my solution. So if I add more F minus, you are in essence adding more of this F minus. So what happens to try and get rid of the F that you just added, it is going to shift to the left. Well, if it shifts to the left, that means more of my solid is forming. Well, if more of my solid is forming, that means that solubility decreases, because solubility is how much of it actually dissolves. Well, if you're forming more solid, less is dissolving. So let's calculate the molar solubility of CaF2 at 25 degrees Celsius in a solution that is 0.01 molar CaNO3 and 0.01 molar NaF. So for the first part here, for A, okay, I have my KSP for CaF2, and I've got CaF2, which is going to be Ca2 plus and 2F minus. Okay, well my KSP here is 3.9 times 10 to the negative 11th. All right. Well, K is products over reactants. My products is just going to be these two. Okay. Now I want to know the molar solubility of CaF2, which means I want to know how much of this is dissolving. Okay. Well, if I have a 0.01 molar solution of CaNO3, I don't care about the NO3. All I care about is that I'm going to add, or I'm going to have an extra 0.010 molar of the Ca calcium ion. Okay. Now when we have this equilibrium, let's remember now, okay, that this is going to want to shift to the left, but my ions in the first part is going to go to the right. So I would normally have X here and 2X here, but I have a common ion, so I have 0.01 to begin with. So I have 0.01 plus X, and then I also have the 2X. So I have 3.9 times 10 to the negative 11th. That's going to be my calcium ion concentration, which is 0.01 plus X, and then I have my 2X squared. Well, I really don't care about the 0.01 plus X because this is a very small K, so I get rid of that. So I in essence just have 0.01 times 2X squared. Solve for my X, remember this is going to make 4X squared. Times that, I'm going to end up with an X value of 3.1 times 10 to the negative 5th. And that is my X. Well, that's the concentration of how much it shifts by, which means that's how much CaF2 I actually have. Because in this case, the X is a concentration, and that is my concentration or my molar solubility of my CaF2. Molar solubility. Concentration in moles soluble. So many moles per liter, that's the concentration. That's all I'm looking for right there is the 3.1 times 10 to the negative 5th. Now for B, it's the same thing, although this time I have F minus that I care about. So I'm going to have 0.01 molar of my F minus. So I do the same thing, okay? I'm going to have the CaF2, Ca2 plus 2F minus. But in this case, my F minus is the 0.01 that I originally have. I'm still shifting this way. It's still going to be 2X, remember, not just X. I have 3.9 times 10 to the negative 11th. It's going to be 0.01 times X, and this is still squared because it was squared originally. And my X is going to be 3.9 times 10 to the negative 7th, and that is my molar solubility of CaF2 in that. And notice how both of those numbers are bigger than the original K value, which would make sense because less of it is actually dissolving. Okay, solubility and pH. Okay, solubility increases as the solution becomes more acidic. And let's look at an example here. So if I look at our example, I take the CaF2 again. If I add an acid, so if I make this more acidic, So if I add more H plus, well, what's the H plus going to want to react with? Well, it's H plus, so it's going to want to react with this F minus, because that's going to make HF. So as I add more and more acid, I'm in essence using up tons of this F minus. I'm going to have H plus F minus yields HF. And what's going to happen is this is going to shift to the right to replace all that F minus that the H is reacting with. So it continues to dissolve over and over and over again, which means your solubility goes up. Okay? So if I have the anion of a weak acid, my solubility will go up as my acidity goes up. Okay? If I have a salt of a strong acid, they are unaffected by a pH change. And again, that has to do with the fact that it is a strong acid and it's totally going to dissociate apart. And you're not going to have any, or going to make any of a strong acid. Okay, so let's look at an example. It says, which of the following substances are more soluble in acidic solution than in basic solution? NiOH2. Okay, what's going to happen here is my NiOH2. It's going to fall apart into Ni2 plus and 2OH minus. Well, if I add acidic solution to it, the H plus is going to want to go with the OH. And if it goes with the OH, then I'm going to make water. So it's going to keep using up my OH and my H together, which means it's going to keep going over and over to the right, which means, again, I'm going to be more acidic, or more soluble as I become more acidic. So this one is definitely one that is going to become more soluble. Look at the next one. I've got CaCO3. Well, I'm going to take this and break it apart into Ca2 plus and CO3 2 minus. Well, if I add the acid, it's going to want to go with the negative. That's going to make my H2CO3. Well, that's a weak acid, so it's just going to use up this continually as I add more and more of it. So this is going to want to shift to the right to replace. So this one's more soluble. Look at the next one. This one should be easy because it's the same kind of example as I had before. If you have BaF2, it's going to fall apart into Ba2 plus and 2F minus. Well, the H plus is going to go with the F minus. It's going to make HF, which is a weak acid. So I'm going to continually shift this way as this gets used up. It becomes more and more acidic. So that one's going to be there. But the last one, AgCl falling apart into Ag plus and Cl minus. The H plus is going to want to attach to Cl minus to make HCl. But HCl is a strong acid, so you're not going to make a strong acid. So this one is not. But the first three will. All right, look at complex ions. We're going to talk more about these in a few chapters, but we're just going to introduce them here. Okay, a characteristic property of metal ions is their ability to act as a Lewis acid or our electron pair acceptor. And this is when we have water molecules that will act as the Lewis base or the ones that are donating. So Lewis bases other than water can also interact with your metal ions, and they will dramatically affect the solubility of your salt. For example, AgCl is a very low solubility. It's to the -10th. However, if I add ammonia to it, my solubility greatly goes up. And this process can be viewed as a sum of two reactions. The dissolution of AgCl, so my AgCl falling apart into Ag plus and Cl minus, and then the Lewis acid-base interaction between Ag and ammonia. Well, ammonia has a lone pair, it's a nitrogen, NH3. So that lone pair is going to be donated to the Ag, because Ag doesn't have any extra. So these two combine and make my AgNH3, and it's going to be actual, should be up here, it should be a 2 plus, like it is on yours. That's a complex ion. Okay, you've got a metal with usually water or something else with an electron pair to donate, and then it has a charge. Because there are many things, so it's complex, and it's an ion because that's charge. So what happens is it's going to drive this reaction to the right, whereas the AgCl is going to be continually dissolving because the Ag is continually reacting with something else. So as this is continually reacting with something else, my AgCl keeps dissolving and dissolving and dissolving. Okay, so I have to have this Lewis base or NH3 to react more strongly than actual water, and it must displace the water that goes around the Ag+. Because when something dissolves, water tears it apart and water surrounds it. Well, ammonia is a little bit stronger, so it's going to kind of tear that apart, and we're going to form an actual complex ion, which is this AgNH3 2+. NH3 is what we call a ligand. that is what's kind of attaching itself to the metal. Okay, and when we talk about a KF, and we're going to look at those here on the next screen, that's the formation of a complex ion. So again, this ammonia keeps repeatedly reacting with the silver to make a complex ion. Very similar to how the acid in the last problem keeps reacting with the base to make that acid, to continually use it up and get rid of it. It's the same kind of thing, except for in this case you're making a complex ion. Okay, so we have what they called our KFs. KF is the formation of a complex ion. So you're always looking at it from the viewpoint of forming the actual ion. Okay, so if you see a KF, there's all going to be for some kind of ion that has the charge there with a metal and something else attached to it. And they're always written with the complex ion as the product. Okay. The last thing we're going to look at here is what we call ANFO Tarism. Okay, and we looked at this before. Something is ANFO Tarik. That means that it can act as kind of an acid or a base. So we have some metal oxides and hydroxides that are insoluble in water, but they all dissolve in strongly acidic or strongly basic solutions because they themselves will act as the acid or the base. Okay, so let's look at this first here, and we'll talk a little more about it. Okay, so they dissolve in acidic solution because they contain basic anions. They also dissolve in strong bases to form a complex ion. Okay, so if I have aluminum here, okay, so if I have Al3+, I'm looking at it in the form of a hydroxide. So if I have AlOH3, that's going to react with a strong acid, okay, to make AlCl3 and H2O. Well, that dissolves. Aluminum chloride is soluble, so I can add a strong acid and it will dissolve. Okay, I can also react it with a strong base to form a complex ion. It's going to look like this. If I have aluminum hydroxide, I add a strong base. We're going to add some more OH minus. It's going to make AlOH4 negative. The extra hydroxide group's kind of going to latch onto that aluminum and make a complex ion. Okay, now in reality, aluminum, when it dissolves in water, okay, this is in reality how it looks like this. It's really Al aluminum with 6 waters and 3+, because I have aluminum surrounded by 6 waters. Okay, now as my strong base is added, this is what you have here on your sheet, protons are removed in a stepwise fashion until you form a neutral and water insoluble substance. So we have here what we started out with, okay, aluminum, and in essence it has 6 waters around it. The OH attacks and takes a proton. The OH here takes one of these protons. That leaves 5 whole waters and an extra OH that I took, because I originally had 6 waters. One of the waters lost the hydrogen, so now I've got just an OH, and it's a 2+. Well, if we lose another one, now I'm going to have 4 waters, but I have 2 of them that have their own little H's that they have lost. So each reaction is harder than the one before due to your increasing charge. It's harder and harder and harder to remove a proton as you go down. So you lose a proton, you start up here, this reaction, you continually lose a proton, and then eventually it'll dissolve again. So you can have a form a complex ion, or you can just dissolve it with a strong acid, either way.